Chapter 8 starts out with this great quote from Niels Bohr. Anyone who is not shocked by quantum mechanics has not understood it. So this chapter is the quantum mechanical model of the atom. Quantum mechanics is unlike anything you've experienced in real life. There's no correlation to real life. And you are not going to completely understand it. If Einstein didn't understand it, none of us are going to understand it. I don't completely understand it. I understand enough of it that I'm like, oh, okay, I believe that. That's good enough, right? That's all we're going for. We're not going to try to understand this because it's way too complicated and actually no one fully understands it. So until the beginning of the 20th century, scientists believed that all physical phenomena were deterministic. And what that means is that the present condition determines the future condition. You know, if the train is going north at 55 miles per hour, you can predict where it's going to be, right? Because you know the direction, you know its speed, things like that. But there were a bunch of physicists who became famous, and they found that for subatomic particles, like electrons, the present condition does not determine the future condition. So if you shoot an electron down a path and measure where it lands, and you shoot a second electron down the same path under the same conditions, it will probably land in a different place. It's very disturbing. Things don't act like that. Nothing big enough to see does, that's for sure. So what we're talking about here is the absolutely small or quantum world. Particles in the quantum world behave very, very differently than large or macroscopic particles behave. So when they are not being observed, absolutely small particles, such as electrons, can be in two different states at the same time. And this is not talking about straddling the line between California and Arizona, right? You can stand in two states at one time, right? Two states meaning you could be a wave and a particle at the same time. So one way to say this is that an unobserved radioactive nucleus can be simultaneously emitting a particle and not emitting a particle. It's two different things at the same time. That seems impossible. Electrons are incredibly small. I mean, it blows your mind. So if you think about a single speck of dust, those little tiny pieces of dust that float in the air, a single speck of dust has more electrons in it than the number of people who have ever lived on Earth from the beginning of time. That's a lot of electrons in a little teeny tiny speck of dust that you can barely see. So electrons are part of this very small or quantum world, and their behavior determines the behavior of atoms. So these electrons are so small that we can't observe them directly. We've only got really fuzzy images of atoms, and these are much, much smaller. And then the other problem with observing them is that if you observe them, it affects their behavior. So that's kind of crazy. You know, so, well, electrons aren't alive. How can they tell if you're observing them? Well, of course they can't. And yeah, don't hurt your brain trying to understand that one. So you may have heard of Schrödinger's cat. There's a lot of jokes about this in science. It was a thought experiment. And the idea of this, the goal of this, was just to make it clear how this quantum strangeness does not correspond to things that we experience in the everyday world. So I've got a couple of videos here.
Further ado, we present Schrödinger's cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute, and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I have answer, please?
Hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrödinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant frickin' hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they react to various forces. But then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. Thing to say, what now? My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand. Say you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me here. I'll say that there's a 50-50 chance that one of the radioactives is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of funding the sciences. So there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead, and an equally good chance that the vial hasn't been broken and the cat's just kicking it, wondering what's for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. Because that's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws. So it, just like every other cat in history, is either alive or dead. Schrödinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom has decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrödinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrödinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. And alternatively, the point is that the universe is pretty frickin' weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive, and one in which the cat is dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think create such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below, and I'll, do my best. Also, if you have an idea for I don't think that means what you think it means, please let us know about that too.
So here's again the quote from Bohr. Anyone who is not shocked by quantum mechanics has not understood it. Schrödinger, and he's the guy that did the cat thought experiment, wrote about quantum mechanics. I don't like it, and I'm sorry I ever had anything to do with it. Albert Einstein didn't like it either, and he attempted unsuccessfully to prove that it was wrong until he died, and he couldn't. So we're kind of stuck with it. So the quantum mechanical model explains how electrons exist and behave in atoms, and it helps us to understand the properties of atoms that are directly related to the properties of electrons. And some of things that we could understand using quantum mechanics: why are some elements metals and others are nonmetals? Why do some elements gain one electron when forming an anion and others gain two? And there's others that gain three. Why do they do that? Why are some elements very reactive? Why are some of them practically inert? They don't react with anything. And there's a lot of periodic patterns that we can observe in the properties of the elements. And again, quantum mechanics can help us to understand those things as well.